entire energy system. We are evolving this system to be more flexible and resilient, safe and secure, carbon neutral. And we are evolving too. Hitachi Energy.
Thank you so much to Hitachi Energy once again for supporting us through this conference and sponsoring this particular panel session. Thank you. And I would like to now introduce the panel and invite our panelists. Before I bring our knowledgeable panelists to the virtual stage here, just want to give like a brief context to our audience here. So we are here to talk about electrifying rail hubs and why the future of bus electrification depends on rail station electrification. Now, we talk about electrification all around in this country and abroad, and we talk about transit, buses, and rail applications kind of separately in two streams. And now we are talking about the integrated and the power of integration, what it can bring to the country and to the economy in terms of greenhouse gas reductions, innovative and efficient transformations or energy transitions, and what is in store for us in the future. It's my absolute pleasure to welcome our panelists, Mr. Richard Cartlow, Director, Energy Systems Transportation at SNC-Lavalin. Welcome, Richard. And Mr. Randy Helmer, Vice President, Maintenance at Coast Mountain Bus Company TransLink. Welcome, Randy, as well. So I do want to enable us, our audiences, to hear directly from you in terms of setting the context, so through a brief presentation. So I would invite Richard first to actually deliver a short presentation, and then we will go to Randy and engage in a Q&A session after. Audience, please raise your questions in the Q&A chat box, and we would be sure to get to them in the exciting discussion that follows. Over to you, Richard.
Well, good morning, ladies and gentlemen. It gives me great pleasure to speak about this subject, which is a growing topic and will have growing importance for transport in the future. So, as you've heard Parvati say, we're looking at using electrified rail networks as an enabler for battery electric buses and electric vehicle charging, potentially with other energy recuperation technologies. Now, I'm sure that all of us would like to see our cities as clean and unpolluted as that. And this is one of the technologies that will assist us in achieving this future vision of engineering net zero, which is becoming a very important topic here in Canada. So, how can we use electrified rail networks to enable the integration of road electrification and rail electrification? Well, first of all, the idea is nothing new. I'm most familiar with work that was done by the LRT operator in Edinburgh in Scotland, and the University of Strathclyde, who collaborated on one of the first studies of this sort. And I'm grateful for both of those organizations for making data available to me. Now, there are a number of trial installations that are presently underway, mainly on a lab and small scale basis, but they can be very easily implemented using mainly existing commercial off-the-shelf equipment in the marketplace. Indeed, some of the products we've just seen from Hitachi's advert would enable this to happen. Now, one of the great problems that very large conurbations have is the fact that the electrical distribution system in the city is often very heavily loaded. And for level 4 and level 3 fast chargers, which are needed for route elongation for battery electric bus operation, generally tends to require a medium voltage connection, typically of around about 4 kV or above. And that can be very difficult to package in a city core. and the system, the overlying MV system, could require a lot of reinforcement. Now, around the world, this problem has sunk the commercial viability of a number of electric bus schemes. However, where there is an LRT or other electrified rail system, such as the metro or heavy rail commuter traffic, there is a great opportunity to site bus chargers at combined transit terminals, where buses often wait for longer than traditional stops, which makes them ideal for fast boost charging to extend their range, as they await for LRV arrivals and departures and passengers to embark and disembark. Now, the technology that I'm going to outline here means that that power can come free of the MV network constraints and potentially integrate other renewables into the energy systems of both rail and road electrification, including green energy such as photovoltaic technology, which I'm going to show you can be combined to put to a number of uses. However, let's start with some facts, and let's start with modern LRT systems. As we all know, braking dissipates energy. Now, that can be returned to the contact line or power rail if the vehicle is regeneratively braked, and the remainder of it gets released as heat from rheostatic braking and friction braking. And as you can see, the top right picture is a very large friction brake. And manufacturers of LRVs have tended to minimize friction brake wear by increasing the braking performance through their electrodynamic brake. And as I'll show you shortly, the difference between the amount of energy that can be generated during braking and that can be consumed during propulsion can often be very, very widely different. That leads to the fact that because the trains generate more power under regeneration, local nearby light rail vehicles or heavy rail vehicles cannot use all of that power. And on a DC network, that means the system is non-receptive. So it cannot accept any more regenerative power without increasing the line voltage to dangerous levels. So the brake system on the train then dumps the excess energy into the large brake resistor you can see to the right of the pantograph as circled on the right-hand picture. Now, dissipating energy as heat is bad news. It means that energy is lost as heat and therefore cannot be recaptured and used usefully. And it also means that there is more expense because you're paying for electricity you're wasting. And depending upon your provincial electricity generation mix, it can mean, of course, there's a considerable contribution towards greenhouse gas emissions. So I've talked about this disparity of the traction and brake, and this graph shows a very, very widely sold light rail vehicle that's sold internationally. And as you can see here, the power under traction is approximately 1/3 of the power it can generate during braking. And as you can see from the flat-topped graph there, the braking on the green line is effectively relatively constant and therefore lasts a lot longer and dissipates more power than under traction. Now, depending upon the vehicle type, the receptivity of the system, the recuperated energy can range for lightweight vehicles from between 18 to 60 kilowatt hours per braking cycle, assuming the network is totally unreceptive. We are seeing longer and larger and heavier LRVs now hit the market, where this disparity is even larger. Now, we've been doing some tests on short headway LRT systems that utilize very high regenerative brake performing trains. And these show losses through the brake resistor as high as between 15 and 22%. Now, that's a lot of money to throw down the drain and burn off as heat. So it doesn't take much to see that on a high frequency, high performance metro or LRV system, there's a lot of wasted energy, which translates to dollars and greenhouse gas emissions. Unfortunately, the rather poor graphic at the bottom shows a test on a recent foreign suburban rail system with 8-car heavy rail consists running at relatively infrequent intervals. But that showed that even under the highest loading systems on their network, 14% of their regenerated energy was lost to heat. And effectively, that is all of the peaks above the solid line there and highlighted in the blue box. So this perhaps puts a sense of scale around the fact that there's a lot of energy to lose, but there's now technology to recuperate it. And this is not new. So abroad, there are a number of systems that use inverters to return the excess regenerative power to generally an internal MV grid. I'm using the example of Singapore Mass Rapid Transit, which I'm very familiar with. This is one of their inverters at a substation. They have a very large 22 kV distribution system. And so therefore, the energy returned can be spread across the entire system and used by trains over a very, very wide area, much more so than if the energy was kept captive at the DC level. Now, this is obviously an excellent choice for systems that have their own MV distribution networks, where other loads, such as stations, depots, facilities, which are also served from the MV network as domestic loads, of course, get energy offsetting through the inversion process. Now, separate inverters and rectifiers are giving way to modern technology that uses a full quadrant converter, which is essentially a large version of what you would find in a powerful electric locomotive. So it puts the rectifier and the inverter all in one box. And the most recent application of that has been on the recently constructed Sydney light rail transit system. Oops, my apologies. However, there are a number of systems that do not have the advantages of large interconnected MV systems. A fact of life is here in North America, many utilities are engineered in a way that makes net export from the LRT system to the utility prohibitive technically or commercially. And thus inverting substations have very limited applications where these circumstances prevail. That's not necessarily true of other countries, where they use inverting substations, they export the power in reverse to the distribution system, where they get credited for an export tariff, which effectively reduces their energy bill. And that's a great choice for systems where you can return the energy to the distribution network, and you have a cooperative utility who's prepared to accept it. So, what are our solutions? Now, given the increasing number of high-performance, short headway LRT systems and metros, in countries that do not allow export to the utility, then a lot of energy is getting burnt off as heat. And you can see there, it's dollars and it's bad for the environment. But over recent years, there have been techniques developed to capture that energy to be stored and dispensed later. And it boils down to three main types of technology. Battery-based energy storage, which is shown in the top photograph, courtesy of Renault Energy. The second is, I believe, an ABB supercapacitor-based energy recuperation system. And courtesy of Oxto Energy in the bottom photograph is a mechanical flywheel that can also be used to store energy in a kinetic form. And all of these have seen application in rail and transit applications before. But traditionally, what has happened is that in this diagram, I'm showing an LRV vehicle, and generally it exports its power to an energy store, and then the energy store releases that to help the train accelerate away. However, in order to bring the concept of light rail transit to facilitate battery electric buses, then the proposal is for the energy store not only to be able to return the power to the trains when they need it, but to store the energy for dispensing in a fast charger to a battery electric bus. I'll go on in further detail shortly about how our concept for this system works. Now, given the talk we've previously had about transit centres that integrate bus and rail modes of transport, where battery electric buses tend to wait for longer, then why don't we use that excess energy that we would otherwise waste to charge the buses? Now, okay, your traction electricity costs remain the same until you introduce energy storage. But as I've said before, in many conurbations, the difficulty of obtaining LV connections for level 4 and sometimes level 3 fast chargers that buses can use to extend their ranges and from route charging can be challenging, it can be expensive, it can be difficult to accommodate, or it may require a much more expensive MV network connection that, for reasons I talked about earlier, may well threaten the commercial viability of the system. So, how do we get over these problems and integrate all of this into a workable system? Well, at the heart of this, we need a power controller to control all of the energy flows. Essentially, it's the brains of the system. Its functions are to integrate traction energy recuperation, combine it with photovoltaic or similar green behind the meter self-generation, if that's desired and permitted by the utility and the client. It controls and regulates the charging and discharging of the energy store in specified circumstances, conditions, and priorities. So it could prioritize buses and it could prioritize the LRVs depending on the time of day. And it blends parallel operation with utility LV supplies to offset facility energy consumption, such as the stations and depots where that's allowed. Now, the power controller is intended to be programmable directly or via artificial intelligence on the fly to reflect the dynamic second by second LRT electrical loading and energy storage requirements. As an example, when there are no scheduled buses, then the energy store can be prioritized to use the excess energy to return the energy to the contact line of the LRT or the power rail, offsetting its energy consumption. Conversely, when BEB demand for recharging is high, we can prioritize the stored energy for battery electric bus use. Now, this is intended to be networked with the LRV and bus fleets to develop a constant situational awareness of both systems to reflect real-time delays and perturbations. For example, a battery electric bus unexpectedly low on charge can make the next charging stop aware of its state and that it needs a higher energy demand than normal. Thus, preemptively, the energy store can extract that necessary power to recharge the out of electrons bus, whilst potentially signaling for a replacement bus to be sent to maintain the service. So, this is the overall concept diagram of how we incorporate and mix energy sources and then distribute it. So, first of all, we have the incoming utility power. Now, where permitted, that can be used in parallel with other sources such as behind the meter photovoltaic or other green energy generation, plus what is returned in excess energy from the LRT system into a centralized multi-converter energy storage system. And you then have a numerous range of choices about what to do with that energy. Now, you can store it for redistribution to the trains. We can use fast charging for buses. And at this point, I ought to point out that most LRT DC electrification systems are quite strong. Typically, larger LRVs can consume up to 2 megawatts of power and return up to 3.3 megawatts of power. And that's a lot of energy to store. And given a large enough energy storage system, that means that there's plenty of energy to power buses. However, we have to accept that this has to be scalable. And so it also, given the fact that most level 4 and level 3 chargers are around the 100 to 400 kilowatt rating, that is not a significant amount of extra power to be drawn from the contact line or the power rail of the LRT system or the metro. So, for example, 100 kilowatts is realistically no more than an auxiliary converter on train. And the system has generally enough strength such that you could continue to power the trains while simultaneously charging your energy store. So, having got the energy into the energy store, we face a number of possibilities of dispensing it. So, the obvious one, and the one we're talking about mainly today, is to give these big buses a big boost charge to increase their range, make them return to the depot less often, offer maybe new routes, longer routes, and better quality and environment for their passengers and the city or municipality it's located in. However, it doesn't stop there. You can potentially use that energy to offset your facility power for things like these transit centres and stations.
Richard,
so it's not limited to buses. And of course, with the ever increasing amount of electric personal vehicles, it offers operators such as Go Transit and Metrolinx here in Ontario, with their which I believe are one of the world's largest car parking operators, the ability to offer cost-effective personal EV charging on a commercial basis. So you can start.
Richard, sorry. Hi, Richard. Sorry, can we finish? Can we wrap up in the next minute?
Indeed, I've just got a couple of conclusions to go, and then it's happily over to Randy. So here we are, very brief summary. The high-performance short headway LRT systems adopt very powerful regenerative and rheostatic brakes for for performance and cost reduction reasons. The electric brake is generally higher rated than propulsion converter. In the best systems, we tend to lose between 7 to 20% of the regenerated energy that could otherwise be captured. And that brings about the fact that we can capture and harness it for lots of other uses, rather than just the traditional concept of returning the recuperated power to the LRT contact line. Or you can use the contact line and the LRT power system to be used as an internal MV system proxy, because then you are freed from the constraints of the utility, where they are unable to accommodate fast chargers in city environments. And the system can be networked at numerous levels to do a predict and prevent and operations recovery scenario for both the LRT, the buses, and personal EV transit systems. Or you can offset your energy consumption for facilities and personal EV charging. So I hope that's given you a flavour of the way that we see the development of this technology going. We'd be very interested to hear everybody's views in the panel talk. And with that, I'll bring it to an end, and I'll happily hand over to Randy for his presentation.
Thank you
so very much indeed.
Thank you so much, Richard. You presented a game changer version of what it means for these integrations to happen. And thank you so much for that great presentation. I'm sure our audience would have a lot of questions to discuss in the Q&A session. So without further ado, let me transfer the virtual microphone to Randy now for his presentation. Randy, over to you.
Thanks very much, and good morning. My name is Randy Helmer, and I'm the Vice President of Coast Mountain Bus Company. And it's interesting to hear Richard's presentation, because I'm not going to get into the technical, which I really appreciate Richard doing and sharing, because there's really some insightful information for us moving forward on this, and we'll incorporate that in our future designs. But it allows us to have the conversations with the folks over at Rail when we do want to tap into power, for instance, and we want to electrify our fleet. And so we have a little bit more argument, thanks to Richard, as to why that's such a good idea and how we can come up with some possible solutions. So really great information, Richard. Thank you. So just a little bit of background. Coast Mountain Bus Company, and it's a division of TransLink. And TransLink was created in 1999. And it delivers services through contractors and operating companies and subsidiaries, such as ourselves, Coast Mountain Bus Company, British Columbia Rapid Transit Company, which has the SkyTrain system that they operate. SNC does our Canada line, for instance. And we have the Metro Vancouver Transit Police and West Coast Express, which is a heavy rail commuter system. And Metro Vancouver, it's the largest single transit service in the area in Canada. It spans 21 municipalities, one electoral area, and the Tuassins First Nation. And unfortunately, Vancouver, BC has been making the news for all the wrong reasons. We're currently in the middle of our third atmospheric river of the week, and you saw all the flooding and everything else like that. So it's having an impact on our area, and some minor disruptions to our service as a result. And it's really interesting, because I've been here 6 years. I come from Ontario, and I've never lived in anywhere else where the weather forecast talks about atmospheric rivers, and you go, and that's rain. So pretty significant stuff. Just let me go ahead here. I want to talk about one of the existing projects that we're doing right now. So in Metro Van, CMBC, we're running an electric bus pilot, and it's on one of our routes. It's our 100 route, and it covers 3 municipalities, which includes Vancouver, Burnaby, and New Westminster. And the route was chosen for a number of reasons. And the big one is that we were able to have 3 municipalities engaged in our high-profile initiative. bus electrification, low carbon fleets, that type of thing is really big on the political spectrum, and it's on everyone's radar. So in order for us to do this and capture 3 municipalities and get their engagement through this process, it was really important for us to be able to do that. What we are using in this pilot are called opportunity chargers. I'll talk about those in a second. And they're installed at the Marple Loop, which you see on this chart here. And that is a bus loop on the route. And it's about maybe 500 meters from our Vancouver Transit Center, which is a 400 bus facility. And also it had at the 22nd Street station here. And so we run 2 Nova buses with 78 kilowatt hour batteries, which are relatively small. They get about a range of maybe 75 kilometers, and 2 New Flyer buses with 200 kilowatt hour batteries, maybe about 175 kilometer range on that. And we're in the process, we've been doing this for 2 years, and we're in the process of expanding this. We're going to fully electrify this route with 15 additional Nova buses, but it's their newer version bus with 275 kilowatt hour batteries. And so the beauty of that, the larger 275 kilowatt hour batteries, is that if any of the chargers are down, because we have chargers at both stations, then we have enough capacity to charge at only one end. And so there's sort of a built-in redundancy there, but also when we're looking at our service, if we're running a little bit behind, we can do what we call a turn and burn, and then just continue on and make up some time there. And I do want to point out that 22nd Street here, it is a bus terminus and a loop, and it's also a SkyTrain station along our Expo line. And then if you look just a little bit south on that, where it says this 91A, it's about that location. That's our Hamilton Transit Center. I'll talk about that in just a second. And that's where these buses operate out of. Just a couple of photographs there. On the left is the Marple station, which I indicated was a loop. So we have a number of buses that are servicing, that are being serviced in that loop. And the SkyTrain station on 22nd Street is just in the background where the bus is there. So for battery electric buses, I'm sure you know this, we have 2 charging options. And one of them is a depot charging, where all our buses pull into the depot, and we usually charge at night. It's about a 4 to 6 hour process, depending on the state of charge of the batteries coming in. And we have en route or opportunity charging. It's sort of an interchangeable term. And then the buses that are operating on Route 100, they come out of our Hamilton Transit Center that I talked about. And we have these opportunity charges here located at our loops. Now this transit center, it is a 300 bus facility, and it opened in 2016. And interestingly enough, we've been doing this pilot for a couple of years now, so not very long after we opened the transit center. But when we were looking at doing this, we were thinking about maybe depot charge buses. And so we had conversations with BC Hydro shortly after we opened the facility, when we said, hey, we're going to go electric. What do you think? Well, they indicated that they needed to invest $11 million to upgrade their infrastructure in order to accommodate our power requirements for a depot charge facility. And the catch is we have to pay for that. So Richard was talking about this before. There's a lot of, electrical requirements and everything else. And when you put it into a business case, and when we looked at this one, we said, there's no way we're going to go depot charge this facility, because that $11 million, it just doesn't cut it when you're doing a business case. So as a result, we determined that the battery electric buses that would come out of Transit Hamilton Center, it would be opportunity charge buses like we have here. So the power requirements for these chargers, by the way, is 450 kilowatts, which is fairly small compared to an entire, 300 bus facility where we need to have the power there. So we worked with our corporate planning departments, and we determined ideal locations for these opportunity chargers. And I'll just talk about that in the next couple of slides. And what we did was we determined that these 2 locations were optimal for not only the Route 100, but also for future growth of our system. Because over the next couple of years, we have probably an order of magnitude 500 to 600 buses that we're going to be replacing. And so most of those are going to be battery electric buses. What we're doing is that, you have to build your infrastructure. So the charging infrastructure, we have to upgrade a lot of our transit centers and stuff. So what we need to do is we need to sort of get that planning process in place, and that takes a long time. Ordering a bus is fairly simple nowadays, but it's the infrastructure itself that's associated with it. And so what we're doing is we're transitioning into that, and we're adding CNG buses with renewable natural gas, which we have contracted supply of, which meets our low carbon fleet reduction requirements and targets, and then a number of electric buses. Coast Mountain Bus operates also 262 trolleys out of the Vancouver Centre, which is close to the Marple station that I was talking about. So let's see, this is a picture of the station, of 22nd Street Station here. So just a couple of things. So essentially this was pretty well a retrofit project. So there were some things to take into consideration. It's really encouraging with Richard's presentation this morning as to how we can tap into the power sources and utilize and maximize the use of that, perhaps that power that is being wasted. So that's great news. So what we had here is that, you know, for this presentation is why did we pick the station? And this is sort of obvious, and I don't think I'm going to be sharing any information that would sort of cause you to have sort of an epiphany and say, wow, I didn't realize that. But just from a bus perspective, here's some of the things that we considered and we looked at. Of course, the station here is going to be one of the busiest areas for train and bus passengers, right? So that's critical. We have a large number of buses from different routes that pull into these loops and utilize these loops and picks up passengers and that type of thing. And we can charge many buses on different routes with just one or two chargers. So really something beneficial for us where we can maximize the use of the charger instead of sticking it on the side of the road, for instance, at a bus stop. If we can minimize that as much as possible, we'll be able to maximize our infrastructure for sure. The big thing too is, we also, this gives us the opportunity to build in redundancies. So if you have several chargers located in one spot, if one goes down, it doesn't shut down your entire system. So obviously, you know, a station is a really good spot to put these things. The big thing too is we already own the real estate. So we don't have to work with the cities to either lease or purchase real estate to install these chargers at various stops. And as you can appreciate, when you're doing your business case, you know, the price of land in Vancouver is extremely, extremely expensive. And so for having to procure land and include that as part of the economics of your business case, again, it makes it difficult to have sort of a positive outcome. Maintenance is a big issue on these things. You have to do your PMs, and then you also have to do your, you know, when the system isn't functioning and you have to go in. So way easier to be able to do it at a station here as opposed to doing it on a city street. And we know that a lot of municipalities, they have restrictions on when maintenance can be performed on major roadways. And one of the things that we decided as an as TransLink is that the whole charging technology, the whole charging process for the buses, we're going to keep it out of the customer facing areas as much as possible. So essentially what that means, and what you see in this photograph here at the station, the purple area is where we have our current charger. And what we do is we'll pull into this area, and then our passengers will get off the bus, and then we go through and we charge the bus. And then essentially what happens is once the bus is charged, usually around 3 to 5 minutes, depending on the state of the battery, it'll pull ahead to the blue area, which is Bay 6, and it'll pick up passengers at that spot. So they're not getting on the bus while the charging is going on. We have the opportunity here to do this because we have the extra real estate, but we're not going to have that on all of them. But what we're planning is as much as possible, we're going to do this. So the other one too is that we're adding additional charger because we're adding 15 more buses on this route. So we need to build in a little bit of redundancy there. And we've decided that we're going to put it over here. And this is our layover area. And Richard talked about this in his presentation. And this is where the buses spend a little bit more time than at a typical bus stop, because we also have operator facilities here. So they'll pull the bus over here. they can charge while it's in the layover area. The operators can use the facilities. There's the lunchroom, there's washrooms in here. So the bus will charge. So there's no downtime, or we don't have to add runtime onto this route, which our planners really appreciate. So this gives us, and having it here, it gives us the flexibility of putting them at various locations and deciding where the best location is. When we were looking at doing this project, you know, some of the technology that Rich is talking about is for future planning for sure. What we had to do was we ran a separate feed in here, and we are already doing some upgrades to this location. So we just brought in a separate feed to feed our opportunity chargers. And yeah, the SkyTrain folks, they didn't have the existing power that we required for that. And so that's what we did for a retrofit project, and that's why we did it. So just finally, what we have is that we have some future projects that we're looking at. We're doing some expansion on our light rail system. We're doing the Surrey Langley SkyTrain extension. It's about a $1.3 billion project. So we're working on sort of future-proofing some of the initiatives that we're doing on the bus side. And you need to do that. And, you know, good example is that, well, I'll talk about it here. So we have 1,500 buses in our fleet, and our buses have a 17-year life cycle. It's probably one of the longer life cycles for the transit agencies. And we really don't know at this time all the details on our low carbon fleet strategy. But what you need to do is you still need to figure out what power requirements you need now and also in the future. And that's critical. And so, you know, some of the things that we're doing is we're engaging with the utility right now, and we're talking about what kind of capacity that we need. And what that does is that gives them the long lead times, so they're able to include our plans into the future expansion initiatives. Because as we know, you get a lot of residential and commercial development along that system. So they're pre-planning for that. So if they know what we're going to need for future use, they're going to be able to make sure that they have the power on the grid that's going to be able to supply that. You need to also charge, you need to plan for where your charging equipment is going to go. And again, you know, 17-year life cycles on the buses and stuff. When we're starting to replace those buses later on in the years, we're not exactly sure where it's going to go. But even if it's a best guess, you need to do this. So determine the location of the equipment, and is it going to be at customer boarding? Is it going to be at layover areas? Because in the last slide, what I showed you was one of the layover areas across the road in the loop. So, you know, at minimum, run some conduit. And so that gives you, you know, the ability to run your power at a later date, and you won't have to dig up your infrastructure. So you can imagine the disruption you would have if you have to dig up that loop with all those buses and everything else going through there. So this will minimize it. Not worse, you know, you got the location wrong. So you have abandoned conduit, and that's pretty well it. It's not a huge investment. One of the things we also looked at is that we're separate operating companies, right? SkyTrain and Coast Mountain Bus are two operating companies of TransLink. So we're running dedicated feeds for charging right now, and that's one of the solutions that we're looking at doing. And we're also working with BC Hydro on time of use and reductions in rates as far as charging for infrastructure goes. So having that separate feed and separate meter, for instance, gives us that opportunity to have those negotiations and be able to determine exactly what the power usage is so we can get those reduced rates. Anyway, that's all I have for this. Thanks very much.
Thank you so much, Randy, for that great presentation. And I'm particularly always happy to see the QTRIC Pan-Canadian eBus project featured. And thank you for sharing valuable insights on your experience there as well. Welcome back, Richard. Thanks for joining me here on this virtual stage wherein we are starting our panel discussion. So very interesting presentations, very insightful. Thank you to you both once again. We are receiving quite a number of questions from our audience, and it spans the technical side as well as the transit agency side. So if I may, start with you, Randy, because one thing that I really wanted to ask is, Richard presented like the need for why this is required for us to move forward. What are the optimization solutions? And it's a victory of both worlds, like the best of both worlds coming together. what hope does it give you as a transit agency or a transit agency lead, as an innovative transit agency? What kind of a hope does it give you as you plan the expansions?
Well, I think it, with the technology that Rich is talking about, what it does is it gives us a lot more options and a lot more ability to, I would say, expand at a quicker rate. Because again, your infrastructure is super expensive. And so if we can tap into existing power and that type of thing, we're going to be able to start electrifying a lot quicker. And the big thing is the thing that's holding us back the most right now is exactly that, is that infrastructure. So that ability to sort of take down those barriers is going to provide us with all kinds of new and exciting opportunities and get some conversions at a quicker rate.
Mm-hmm. Awesome. So on that point as well, Randy, if I may turn to Richard on that infrastructure piece, because you highlighted the capital expensive side of it, but we are talking about technology, and our audiences were also wondering, from a resiliency perspective, what is that single point of failure within the LRT BEB network that you can think of, like that we need to plan for, and a transit agency like TransLink may need to plan for?
Absolutely. I mean, I think it's important to realise that energy stores can be quite expensive, but they're incredibly versatile. Here in Canada, all of our LRT and metro systems are specified with very, very high levels of reliability. Generally, they want the system to carry on with a complete failure of a single substation. Now, that would not impact the ability to continue to serve the chargers at stations, for example. We may have to turn the rate down because of the increased power draw from the substations that are still online. But substation equipment failure is very rare. I think the principle we have established is to have a number of levels of redundancy in the charging and energy storage technology, achieved in an economical fashion, so that minor hiccups don't wreck Randy's service. There's still a lot of development work to do. It's still very much at the infancy stages. But we would be aiming for a sensible balance between reliability, economy, affordability, and ease of implementation. And that might mean different approaches for each agency, depending upon their own particular requirements, and maybe the nature of their LRT system as well. I mean, all of these would require quite in-depth studies to come up with the right answer.
Mm-hmm, mm-hmm. Indeed. And I think the idea is pretty clear, particularly you highlighted the versatility aspect as well. If I may turn to you, Randy, because you mentioned in your presentation as well about the fact that you were having real estate to play with, and in our work at QTRIG, when we work with different transit agencies, the real estate constraint is a solid one. And I do want to pick your brains a little bit on that particular aspect, and how you see that real estate constraint to play in if we are talking about such an integration in the future with respect to battery electric buses and LRTs, not about 2 buses, but about the 1,500 buses that you would be having. How would you envision some challenges, and what are some mitigation efforts around that?
That's a good question. There's a couple of challenges that we have with respect to real estate. One of them is that even at our transit centers, for instance, if we're going to do the depot charging, you need to be able to get that technology in. And so that takes up some space. So our tracks, for instance, and so you're going to lose some space there. And we have 7 transit centers, and we're at or near capacity on all of those. And so to lose, a number of tracks in order for you to put that infrastructure, that presents a problem. Is that can we get additional real estate adjacent to the existing facilities and stuff like that, which is a real challenge. So there's that challenge there. And then there's obviously trying to pick up the real estate with the cities. And so I talked about this, the Q-Trick pilot that we're doing covers 3 municipalities, and that's that engagement that we're getting with the municipalities. And so it's highly political, right? And so the more engagement that we get early on, the buy-in that we get. And so when we're going to the municipalities and asking for, some space on the street and that type of thing, then we have that buy-in, if you will, because it is a big initiative. We have targets for 2030, 2040, and 2050, and it's all been endorsed by our 23 municipalities. And so we know they're all in on that. So that gives us the ability to do that. It's adjoining property, private land, and that type of thing that's created a little bit of a problem also for us. So your solution is going to be, whether it be at the transit center or possibly putting in overhead infrastructure to do the charging, so it doesn't take up those tracks, or going directly to the municipalities to get the properties. We've been pretty lucky, but it's a long process, right?
It is indeed. And, I think you indicated how important it is to bring like different stakeholders, different parties as well in your presentation and in your response as well. Particularly, if I may turn to you, Richard, on the utility side, this is partly technical, partly stakeholder management, because you talked about how, other jurisdictions across the world may be doing it in terms of utilities having this ability to kind of recoup power and, get it back to their grid or whatever. And it may be restricted in North America. So in that particular circumstance, how can we engage with the utility? And in our electrification planning, usually at Q-Trick, when we do consulting, we always recommend and we engage utilities at the start of the process itself. And it's very important that they are, engaged. So how do we transcend that barrier that our utilities may be facing from a prohibitive standpoint?
I fully agree with you. The early involvement of the utilities, or potentially, with the technology I've described, a potentially separate rail operator is absolutely vital. A lot of the reasons for the North American system to be less receptive to exported power is just as a result of a divergence in electrical engineering philosophy that took place in the early days of providing electricity to cities. And often, the tramways were the first electric service in a city. This is nothing new. I'd like to quote the example of Australia. So Australia has the world's highest proportion of what's called non-synchronous generation. So they have more inverter-based resources than any other country. And we're going to see an increasing use of inverter-based resources here as the energy revolution takes over, not just in our field of transport, but in the greater energy market itself. And that is going to have to drive technological change. We have seen a number of studies come to market from transmission and hydro companies to look at what changes are made. And some of them are relatively simple, others are more complex. And unless you have a very, very large utility with a uniform approach to this, it can be a bit of a patchwork quilt, because each municipality or privately owned hydro system will have developed itself in its own way and will have rules. And in certain provinces, even the commercial arrangements make the return of energy difficult, even if it was technically possible. So I think the energy revolution is going to drive, the wider energy revolution is going to drive technological change that will make this more acceptable, more accessible, and more achievable. But it could well be that we might be in the vanguard of this in transport. because we're thinking about this already, and we're starting to develop solutions, in conjunction with people like Randy and Kutrick and all of the other contributors to this conference. So it may be that we have to set the tone, particularly for the hydro companies. And as you say, early stakeholder engagement. And I think the other thing is that there is a significant education piece on this, because a lot of this technology has yet to penetrate the North American market, unlike the Australian one. And so we're still at a very much early learning curve stage.
Right. So that is very insightful. Thank you, Richard. If you do not mind muting yourself, thank you. So I think that picture is very clear. Like, we have the technological evolution or the revolution, as you say, happening. There is a versatile option out there. There are stakeholders who are willing to contribute. If I were to in the last few minutes that we have remaining, if I were to equip you both with a magic wand, so with that enables you to have the ability to expedite the change that you want to see in your transit system or in the economy, in the country, what would you do with that magic wand? And it is endless scope, let's say. So if I were to give you that magic wand, Randy, what would you do? What would be that one change that you would expedite using that wand?
Wow. Interesting. Well, I think, well, you look at our system, and so one of the things we also do is we operate 4C buses. And so we're looking at the technology of, we need to do our next build. We just launched one in June, and we're working on the design for the next build, and we're looking at all electric. And so it's being able to incorporate all modes of public transportation. And in this case, I'll say electric, but it can include other technologies for low carbon fleet. But being able to do that in sort of a quicker fashion and in a more integrated fashion. So what we can do is that our C bus, for instance, operates down at our waterfront station, which is a beautiful, massive station. And we have Canada Line coming in, we have Expo Line coming in, we have C-Bus operating out of there, we have buses out front, and we have all of that. And to be able to have that all operating, all electric, and be able to do that over the next couple of years, that would be the magic wand to be able to do. And we would be, we'd be so far advanced and in a much better place for sure.
Beautiful. That's a great way to put it. Thank you, Randy. And Richard, you have the one, but you have only 30 seconds to use it. So go for it.
I'd like 3 magic wands. First of all, I'd like the magic wand to help Randy electrify his complete system. Secondly, and I'll finish on this point, is that I think we need a unified set of standards and approaches across Canada for this, because that will drive down the costs for everybody. I've recently had the pleasure and the privilege of being elected as the chair of a CSA Railway Electrification Standards Committee. And I'd like to throw my magic wand at the CSA to say, right, get your heads around this and get a committee formed, get consensus across the country, get the same standards, and drive down the costs for every customer.
Awesome. Thank you
so much. With Kutrick as well.
Thank you for including us in there, because we are leaders in the space. Thank you, Richard. Thank you, Randy. Of course, I cannot grant you the magic wand. I do not have the powers, but I think we have the technology, we have the knowledge, we have the right minds and the right brains to put this technology to work and move our future forward. Thank you so much for sharing your insights. Really, really appreciate the discussion. And thank you to dear audience for tuning into this particular session as well. We have interesting sessions happening all throughout today, and please do join our networking session at 3 p.m. today as well. Thank you, and have a great day.